watching. Okay. Okay. If you see them during the session, please tell them to connect to the Zoom and come with their laptop and share the screen in order to save some time and have more time for presentation results and discussion. So I would like to welcome you all, either physically or online, participating in this session for data-driven solar forecasting. Our first speaker is Yann Fabel from Lidar. Yann, the floor is yours.
Well, thank you very much for the nice introduction. I hope you recovered well from yesterday's dinner. So yeah, let me start right away. Today's topic is leveraging generative models for enhanced solar irradiance ramp detection. So this talk, why doesn't this work? No. This talk is followed as structures, as structured. It's structured as follows. I'm going to start with a short introduction in state of the art, but I'm going to do this very fast because I think you've heard this enough already the last days. Then I'm going to present our generative nowcasting approach, which is quite new. So we are not the first ones applying video prediction for sky images, but I think I've only read about one paper from last year, and we have a bit of a different approach. And I'm going to dive into ramp event validation, because that's what we're focusing, or what we want to improve by this generative nowcasting approach. And I'm going to finish with a conclusion and outlook. So to the introduction. So the motivation, of course, is, first of all, let me clear up or tell you what we define under solar ramp events. So as you can see here on this short video, sudden local changes in solar irradiance due to cloud passings cause these solar ramps, and or are those solar ramps. And the effects are that local generations can also fluctuate quite strongly due to those solar ramps, and especially negative ramps might cause, for instance, grid code violations. So what we want to do is anticipate those ramp events in order to have an increased awareness for the plant or grid operator, and maybe also to minimize the requirements for battery storage. But for this, of course, we need cloud information in very high resolutions, spatially as well as temporally. And as you already saw on this plot, I think at least twice, all sky images are the best resource for that. And what do we understand by all sky imager nowcasting? So we have this sky imager, which is a ground-based camera with fisheye lens, and we apply some image analysis. And there are typically three categories of how we can do this image analysis. First, there's the physical approach, where we explicitly model the clouds, their motion, and their transmittance. And there's a data-driven approach, where we try to train a machine learning model to learn the correlations between clouds and irradiance directly from images. And of course, we can combine both approaches in a hybrid model. And that's also what we did earlier, or before this new generative model. And yeah, as a result, we get a multi-step intra-hour irradiance forecast. Yeah, so just a few words about the hybrid model, because that's what we are going to compare our generative model with in terms of ramp event detection. So this hybrid model is also a blending model, as we have already seen in presentations from yesterday, but here we only use sky images. So we have this physical model where we have a stereoscopic view of the sky with two cameras. We model the clouds in 3D. We obtain the motion vectors from the images, and yeah, extrapolate the clouds in space and time, and yeah, apply shadow projection, and then thereby get a shadow map actually. So not only a point forecast. And then we have two other models, the persistence model, I think you already know, and the deep learning model. It's an end-to-end trained model where we train a machine learning model using a sequence of images and sequence of time series data to generate a multi-step point forecast. And these individual forecasts are then combined using also a linear regression approach. So for each lead time, we get a global weight for each of the individual models, which then is combined, and we obtain our hybrid nowcast. And there are some advantages doing this hybridization. So we can combine the strength of both worlds and achieve better error metrics and especially forecast skill than each individual model would obtain. And yeah, in the end, we figured that it's a well-suited model for predicting average GHI. But there are some disadvantages because, first of all, we lose a bit of interpretability because only the physics-based model is really interpretable. And by combining it with other models, you don't really know what's happening anymore. And the bigger problem is actually that it leads to further smoothing. So persistence and also the deep learning model trained in an end-to-end manner, it just generates rather flat forecast curves because the deep learning model is already optimized on MSE, and the hybridization is also focusing on reducing MSE. And this just leads to limited capability to predict ramps. And this is what I just want to show you here. So as I mentioned, it is good in RMSE and forecast skill, but may not really catch the ramps. And if you look at the plot here on the left, so that's a plot for a fixed lead time 10. And as you can see, many times it just looks like a persistence plot. And I think you have heard this as well already. That this is a problem we are facing. And if you look at this individual forecast, so at 9:10, you see like one forecast for 20 minutes. And you see that it gets the trend more or less, but it has not any fluctuations. And that's the reason why we are now focusing on a different approach to actually catch those ramps also with data-driven models. And here we now came up with a two-stage method. So we first predict future sky images in a separate model, and then using another model to predict the irradiance from those future sky images. And yeah, for the first model, we use a generative model, a so-called diffusion model, and use the recent sky images as an input and get as an output the next images. And we can evaluate each image individually. And there we have another advantage. Like, first of all, of course, we model the cloud motion implicitly by the generative model. We have an increased interpretability because we have this synthetic image as an output, as an intermediate output. And we can also model uncertainty to some extent because we can sample different futures from the input image. So therefore, I maybe need to go to the next slide, because this diffusion model, it's based on generating synthetic data from noise. So it actually learns to the reverse process. So you add noise to your data, and the model learns to so iteratively. So I don't really want to get into much detail here, but actually the benefit of this diffusion model is that you can generate different samples by just sampling multiple times Gaussian noise. And maybe we can just look into some of the intermediate results, like the synthetic images. On the left, you see the real images, and on the right, you see a mixture of real and synthetic images. So when the margin is green, you have the input, and that matches, of course, the reality. And for all samples, as soon as it turns red, I think someone is not muted. then you see the synthetic images, and we tried this, or we looked, obviously, into different sky conditions. And while for the first two rows, all the samples look quite similar, when you have some convective clouds, actually, there you can see that also the samples vary a lot. So yeah, I don't know if you see it well here, but yeah, there the three samples deviate quite strongly, and also they do not match as much the reality anymore. That's actually what we want. We want to know when the model is uncertain, and that so that we get a bigger range of possible futures. And then coming to the next model, which is the Irradiance model, so the second step of the generative nowcasting approach. Here we have just in this simple approach we're right now. So these are more or less all preliminary results. So at this stage, we are using just a simple regression model using a CNN architecture. And yeah, we process each of these synthetic images individually. But for training, we're actually using real images. We try to simulate the characteristics of the synthetic images by resizing them to the same size and adding some noise to simulate the characteristics of the synthetic images. But yeah, we train on real images, and for the validation, we use real as well as synthetic images. And yeah, just to give you a preview of how it looks like. So here we can see in yellow the reference GHI curve, and in green the curve for the predicted irradiance from real images. And in blue and also shaded blue, we see the median from the samples using the synthetic images and also the distribution. So you don't really see a variety here because it's just lead time 1. But I just want to show you that we actually can see ramps that are strong, like here in this case. And if we look at if we compare the real images to the synthetic images, we can see that, okay, this cloud is just passing through, and the sun disk is becoming visible again. And that's why, yeah, we were actually able to catch this increase. So now we wanted to evaluate this also quantitatively, and therefore we need a definition of ramps. And in general, they depend strongly on the use case. So there are existing definitions, but often they're either complex or too sensitive. So we wanted to focus on strong ramps. So we came up with a simplified definition here. So a ramp in our case is if the change of GHI over a time interval exceeds the threshold in watts per square meter. And if there exists a ramp in the forecast horizon, so this is 5 minutes in this case, we have a ramp event. So like just as an example, in this curve, you can see at 9:15, okay, in this yellow triangle, the change of GHI in 1 minute is greater than the threshold of 100 watts per square meter. And this is why for this forecast, we have a ramp event. We validate this against on-site measurements from GHI. So if a predicted ramp event was also observed in the measurement curve, then we have a true positive. As I said, we use only 5 minutes as a forecast horizon because that's currently the limit of the diffusion model. And yeah, we use those confusion measures, as you can see here, and also the F1 score, which is a combination of precision and recall as validation metrics. Here you can see on the left the results from the hybrid model I presented earlier and the results for the generative model. And as you can see, so the goal would be to have 100% on the diagonal. But as you can see, the hybrid model for both thresholds of 50 watts per square meter and 100 watts per square meter is not really capable of predicting those ramps, especially the ones that are stronger. So on the other hand, the generative model has quite a better distribution. So it's still not perfect, and there are different reasons for that. But we actually improved the potential of detecting ramps quite a lot while maintaining a high rate of also not generating too much false positives. And I just want to highlight here again that the selection of threshold is a bit arbitrary, so it depends really on the application and the technology. But we chose this to show that we are actually capable of detecting ramps independent of the threshold. Oh, we're getting better. And this is also seen in the F1 score. Yeah, so, but we have seen some problems, and that's not only on the synthetic images, but also on the real images. And that's because of oversaturation. So the interesting area in those sky images is close to the sun, and so the circumsolar region, and there we have just a large region of oversaturated pixels. So here in this example, you can see two images where at the left we have double the irradiance than on the right, and for the human eye it looks quite the same. What we now want to do is to lower the exposure times in order to lower the amount of oversaturated pixels. And just to give you an example, we trained like the same model with the same configuration. So everything is the same, just the images were on the left plot. You can see the images with a 160 microseconds resolution, and on the right an 80 microsecond resolution. And we just reduce this bias a lot, where we are not quite 100% sure where it comes from, but our guess is that due to the large amount of oversaturation and higher exposure times images, the model is just unsure and is more conservative. So just to mention again, these are evaluations on real images, but because we have to train the diffusion model again with lower exposure times, but we can already see that for real images, we're getting better in detecting those high irradiance values as well. So to conclude, I presented a few things. So the quality of nowcasting models in general depends on the use case. So data-driven and hybrid models, as they have been developed so far, are quite good in achieving good error scores, but they may not be well suited to detect ramps as well, because they are optimized in RMC. So I presented a novel generative approach with sky images that uses a diffusion model to predict future sky images and a separate irradiance model to derive the GHI or whatever irradiance from the synthetic images. And then I just showed you some preliminary validation of this ramp event detection and compared it with the previous hybrid model we've been developing. And we've seen that the hybrid model, while the hybrid model misses most of the ramps due to the flattened nowcast curve, this new model is quite good in detecting the ramps while having also just few false negatives and false positives. But of course, we want to improve this further. So as I already mentioned, we want to train also diffusion models with different kinds of images with different exposure times. And we need to reduce the training effort because, as I said, we're currently limited to those low resolutions where we lose just a lot of information from the clouds, and also a short forecast horizon of only 5 minutes. And I don't know if you heard about Sora from OpenAI. It's quite a new diffusion-based video generation model, and it's quite impressive how realistic they can get. And that's what we try to integrate, like the techniques they use. And for the irradiance model, we also want to get better because we can still see that there's quite a gap between predicting from real images would be the perfect forecast from the video prediction models. And there we want to include some features to also get rid of the bias that we've seen, and try some more complex architecture. So maybe not just CNNs, but also some transformers. And yeah, maybe not only using one image with the fixed exposure times, but multiple images, or maybe also HDR images. Yeah, that's basically it. So thanks for your attention. If you have questions, feel free.
Thank you, Yann. May I use one of the microphones, maybe? Okay. Okay. Thanks again, Yann. Any questions, please?
Yes, I have some questions. I put them in the chat. Can you answer them?
Sorry, yeah, we have a question from the audience. I will repeat it because I think you don't hear it, and afterwards I come back to the question from the chat. So
Oh, thank you very much, Yann.
Can you just repeat the question, the second question? Okay, so the first question was, I think, regarding the computational resources that are required and the limitations, and also the data set, I think. Okay, so we're currently, this model has been trained with about 1 million images, if I'm not mistaken, a bit less. But yeah, it took like 2 weeks of training with a huge cluster of 4 GPUs with each of like 40 gigabytes RAM for memory. So it was quite intensive, and we want to reduce this, for instance, by applying diffusion not on the image space, but on the latent space. There are some few techniques. I think we can talk in detail more later. And the second question was, again, I missed it. Can you repeat it the third time?
Task, train your model on computer images to go into the digital space. Then when you generate generative images, do you notice any
yeah. Yes. Actually, so for lead time 1, which is even one, we haven't like compared it to, like we don't create synthetic images for lead time 0, so it's always like 1 in the future. But for lead time 1, it's quite similar, the results also, like when we look at RMSE and MAE. So there's not a big gap, but if you go further in the future, of course, the gap gets greater because the videos are not matching as well anymore, or the images are not matching as well, the true images anymore. But actually, the model is quite good, even in such a low resolution, to estimate GHI from synthetic images. Okay, so if there's time, I don't know, we'll...
Let's see if there is any. There are a couple of questions also from here. But let's go to the...
okay, why the choice of 50 and 100 watts per square meter in minute as a threshold? This was because we had some preliminary studies on how big ramps have to be in order to cause some problems in PV plants, but that depends on a lot of factors. So we couldn't really just say a GHI ramp of 50 or 100 watts will cause a problem in the PV plant, because, as I said, it depends on more factors than just the ramp of GHI. So we just chose those 2 to have a wider range, but it's kind of arbitrary, I have to admit. And I think, yeah, the second question, the presentation will be in the Dropbox.
Thank you. Very clear.
So the third is also a quick question in terms of RMSE, bias, and MAE. How does it compare to the initial hybrid model? It's worse, so it's not as good as the hybrid model, but we're trying to get better at that. But since these are not final results, I didn't want to show you any preliminary results on this, because it looks a bit, especially due to the bias, which we haven't completely understood yet and solved. We get also bad RMSE and MAE. So I think now we have to continue with the next speaker.
Okay, there are more questions, don't worry.
Oh, okay.
So where is the first one? I will give the microphone to make it a little bit easier.
I just have one question with respect to your hybrid model. It's fair enough that you want to focus on the on your other model, but I think if you compare something that is tuned for RMSE in a ramp event, then it's clear that it cannot compete. So if you optimize with RMSE, you do exactly the wrong thing. But if you would optimize it in a different way, the hybrid model would still maybe be much better. So maybe you could, I would at least recommend that this is presented a little bit different, because I think it doesn't make sense, and nobody would optimize a ramp model with RMSE.
Yeah, it's a fair point, I think. So I just wanted to highlight that with a new model, we are actually able to do this. While, yeah, I think it's kind of obvious for some people, but for others, I think it isn't that obvious that these hybrid models are just not well suited for this. So I just wanted to show this in numbers. But you're right, and like for deep learning models, actually I don't know about any work that doesn't optimize on RMSE with respect to irradiance prediction. So if you know anything, let me know. I know there are metrics, but I haven't seen any work where where actually optimizing the deep learning model on a different way than MSE. So that's why most of the data-driven models are good, maybe in RMSE, but not well suited for ramp event detections. And for the hybrid approach, yeah, maybe there would also be the option to just combine it using a different optimization than RMSE, but we haven't looked into it. But I think it's a very good point that it's not a fair comparison, but it shouldn't be like we don't really want to compare it like that. I just wanted to make it more clear.
I wanted to ask, I think you mentioned that you're currently limited to 5 minutes forecasting horizon, but why is that? Or couldn't you just use your model recursively to extend basically as much as you want?
Yeah, well, I think you could do it like in an autoregressive manner, then use just the output from the previous forecast as an input again. We haven't done it, but yeah, the problem is that it doesn't scale linearly. So if you use more data as an input and want to get more as an output, it just gets computationally much more expensive. And as we already for this first model with this simpler configuration, we have to train so long, we just want to do a different approach and be also more flexible in this sense. So we don't want to have a 1 minute resolution if we go, for instance, 1 hour ahead, but maybe for the first 15 minutes have this 1 minute resolution in forecast horizon, and then maybe only 5 minutes, and then maybe 10 minutes, and then we are getting more flexible if we just switch or change a bit of the configuration.
Okay, thank you so much. Coming down for the next speaker, I would like to have a question too.
Okay.
You saw us a couple of figures with different watts per square meter. The same picture, almost the same picture, but there were one in that case was 100 watts per square meter, and the other was 200 watts per square meter. Can you show us that slide too?
You mean?
Yes, the previous one. This one. I'm wondering, for your model, do you use the full image?
Yes.
Do you not crop it at all?
Well, I crop it to the fisheye lens part, but I don't crop it to the circumsolar region. I use the full image.
Okay, so you just cut the black areas.
Yeah.
Okay. If you lower this exposure to 80 microseconds, could you be able to get enough information from the clouds to have a forecast for the next 5 or 10 or 15 minutes? It's going to become too dark. And if you go to HDR, did you try it? I mean, how much time do you need in order not to create some kind of ghost effect because of moving clouds?
Yes. So actually, what you see here in the 80 microseconds plot is that for really low irradiance values, the images are really dark, and there you have actually a quite deviation from the predicted and the reference curve. So as I mentioned in my last slide, we want to maybe integrate multiple exposure times for a single model, like for a single timestamp, to like have still the high amount of detail around the sun, but not too like also much information or not too dark information on areas that are not close to the sun. And I think the problem with the HDR image is valid because in the first tries we did, we saw that it's actually worse. And I think that's because the model relies a lot on the brightness, and yeah, this is not the same anymore with HDR images. So maybe there can be a benefit. Also, we haven't tried it with our own HDR images where they are always created the same, but with an automatic HDR, like the one we just get from the camera. So there are some configurations we still want to try out, and we haven't already, we can't say yet what is the best input to get the best irradiance estimate.
Thank you so much. And so time for our next speaker, Rafael. Is there any of the rest of the two speakers here today? No, one. Oh yeah, here you are. So Miss Angela, okay, let's see, maybe she will come until the end of the session. Well, oh, hi, sorry, I haven't seen you. Yeah, great.
Okay. Okay, everything's set up. Okay, perfect. Do we see? Okay. Let me get rid of this guy. I know I have to exit. It's in the other computer. Oh, okay, thanks. Okay, sorry for the interruption. So hello, thank you for hosting me. I'm Rafael Carillo. I'm a senior scientist at Jie Yan in the Digital Energy Solution Groups. Today, I'm going to try to speak about graph machine learning for short-term solar forecasting. So given that the title of the workshop is minute scale forecasting, actually, my work lies actually up to 6 hours ahead with a resolution of 15 minutes. So please bear with me. I'm still in the minute scale, but I'm not really a very short time scale forecast. So it's a 15-minute resolution forecast with 6 hours ahead. So that's, sorry, just to grab the expectations. Now, typically for short-term forecasting, the best way is to combine numerical weather models with satellite images, propagate the clouds, and have some ground-based sensors to calibrate the measurements, and that gives a very good result. However, in order to have good numerical models or to solve it in a good spatial resolution or time resolution, it might take a lot of computational complexity. Now, one question that we ask is, can we do it only with ground sensors? A little bit like what Rodrigo presented yesterday. So what if we have just 2 sensors, for example, a PV system that is looking at the clouds, and if we know that one cloud is passing in one station, or we sense that a cloud is passing, then if we know the speed and if we know the direction, then we could say, okay, it might be passing in the other one. Now, what if we have a third sensor, a third PV system? So these guys, they could speak to each other. Let's say they want to, okay, there's one coming from the north, one's coming from the west, and it could be, and so forth. So the main idea that we do is to track the cloud motions, or to try to predict either PV power or irradiance, looking at different sensors in time. But now one question comes, what happens if we have a dense network of sensors? So here we have 3, but what if we have more? If we have more, we could have an improved spatial resolution, and maybe a time resolution if we have enough time resolution from the time series, but also to deal how to process this, or how to model these changes. So the kind of models that we resort to are called graph neural networks, and graphs are machine learning models for networks. So here I'm showing 2 different versions. So on the left or right, it's a picture of Paris. In Paris, so there are the river, the parks, and the picture shows many information, but maybe it's not like centered information. Now, on the other hand, on the left-hand side, I show a picture of the metro of Paris, and this picture, it shows you how to get from one point to another using a specific metro line. And this is exactly what a graph is. A graph is an abstract model that tries to show or model relationships between 2 entities, or between 2 nodes, as it's called, and this relationship is called a link. So in this way, we have an abstraction of the models, and this is exactly what we use to model the spatial temporal relationships of the data. So now, what do? We have a ground dense sensor network. This sensor network can be PV systems that are measuring power, or it can be weather stations, and we're measuring irradiance, wind speed, wind direction, relative humidity. And then based on this measurement, we try to track the clouds, basically, and we model it as a graph. So basically what we do is we try to basically track the dark dots in the picture on the graphs. But we don't use a single snapshot. Of course, we use time series of past data from this in order to track the spatial temporal relationships of this. Now, one challenge that we also have when we deal with real systems, it's data quality. So most of these deep learning models, they're pretty nice, let's say, but they consume a lot of data, but especially they require quality data and clean data. So if we have data like this, it's wonderful, there's no problem. But most of the time, from real systems, you don't get quite nice data. You have gaps, people go on vacations, they turn off the Wi-Fi, or simply there are communication gaps, and you don't get complete data. So you need methods also that are robust to this kind of system. So now that's what we've developed, and we call it the Generative solution. It's a solution for short-term probabilistic forecast for 6 hours ahead with a 15-minute resolution. And it receives first as inputs data from either weather stations or from PV power systems. And the first block, it's called like the heterogeneous data embeddings. So what we do is we take data from these 2 heterogeneous sources, and we embed it or project it into a common space where they can live. They can be fused or mixed. And now, based on these dynamic features, now these nodes are changing or could be changing at every time, because we can have appearing or disappearing nodes or data. So what we do is, in order to make it more robust, we take up this dynamic feature extraction. So nothing really fancy, it's just a clustering on the space. And based on this clustering, what we do is this, we have a centroid assigned for this cluster. And based on this, and based on the local topology, I don't know if you can see my mouse, yes. Based on the local topology of each cell, for example, we create a subgraph, and based on this subgraph, we extract the relevant features for the nodes that are available at that time stamp. And based on this, we aggregate them in with a graph attention neural network, and we create a representative for the node or for the representative node. And now, based on those representatives, now with a fixed network, we create a forecasted model based on also on a GNN for this fixed network. And then we forecast features for all the lead times, for the H times steps ahead. And now based on these forecasted signals, we also train like a graph interpolation model that can receive as query points on, well, any location, let's say in Switzerland or in the region of interest that we have. And then we produce an estimate of the forecast in the points of interest. And but one thing is that we produce also like probabilistic forecast on that. Now, coming a little bit on the GNNs that we use for the forecaster, we use encoder-decoder models. These encoder-decoder models are sequence-to-sequence models, as it's called. They are autoregressive models, but they just don't predict one step ahead. They are trying to predict H steps ahead. So it basically takes a sequence from before. In this case, we take a sequence of 4 hours in the past. So then that would be like 16 steps in the past. It processes in the encoder. The encoder basically creates a representation of those time series for all nodes available in that time. And the decoder takes that representation. We also use the clear irradiance as an input in the forecast horizon. And then it mixes that and it processes and produces a sequence output of the 6 hours ahead. Now, for both encoder and decoder, we use architecture that's called a graph convolutional long-term memory or graph convolutional LSTM. So now graph convolutional layers are there to diffuse the spatial information between the nodes. So if you're familiar a little bit with the convolution, for example, in time, it basically takes like a kernel and it tries to do the convolution of a small kernel in time. In 2D, it's also good because you can convolve like a small kernel with a patch in a regular grid. Now, in graphs, it's a little bit more difficult because there is no sense of grid, there is no sense of shift. In graphs, it's an irregular domain, but you can still define convolution there. And the main idea is to define it through message passing through your neighbors. So you just speak to your neighbors, aggregate information from your neighbors, and then you pass it around at every time. And that's how you diffuse the information between nodes. Now, the LSTM is a type of recurrent neural network. And the LSTM is there to model the temporal relationship. LSTMs are sort of like nonlinear state space model. So the encoder and decoder, let's say, are both like LSTMs that are run for the sequence, for example, in the encoder for the 4 hours or 16 steps, and in the decoder for the 24 steps ahead. So in that way, when you're training an end-to-end, you are training to predict the sequence of 6 hours ahead. We also modify like the output layers and the regression, and the loss function to account for quantile regression. So we train to produce quantiles instead of having like an RMSE or an MSE loss function. We have a quantile or a pinball loss function to produce, I don't know, Q quantiles that we would like. Now, right now, what we produce is the 50% quantile, like the median value. We also produce the 95% percentile quantile, and the lower bound is the 5% quantile. Here I have some plots showing from the same day for 4 different times at 6 a.m., 9 a.m., 12, and then at 15. But one good thing about this is that the system can be adapted. So you can produce as many quantiles as you would like. You can easily modify the architecture to produce more quantiles if you like. You can produce also less conservative confidence intervals. For example, if you want to do economic optimization, and it can be easily modified. There's no a little bit of retraining, but not that much. Now, a bit of a quantitative evaluation of the probabilistic forecast. So reliability, it's an important quantity to forecast. So we see that the PICV or the prediction interval coverage probability, it's good. But we know that reliability is nice to have, but it's not the whole picture. So we also use the continuous rank probability score to, or normalize, peak normalize rank continuous rank probability score to evaluate the probabilistic forecast. We evaluate them on 1 year of historical data. Now you see that it can follow more or less the quantiles with always CRPS of less than 6% for the entire forecast horizon. I'm going a little bit more on the comparison. We compare also on 1 year of historical data with two approaches. One, in green, is the smart persistence model, which is very good, let's say, for 1 hour ahead. And the red curve, it's a commercial cloud propagation system, which is also quite good. And in blue, we see the results. So we see that from the first 2 hours, like both approaches, like the cloud propagation and our method, compares basically almost the same. But after 2 hours ahead, there is an edge of having this. We have a live demonstrator in Switzerland that yields forecasts for this time. This demonstrator has a small network. It has only like 130 stations, whether coming from Meteosat in Switzerland, and around 64 PV stations. That's more to have a demo for real time. So it can predict irradiance over all Switzerland. And there is an API available to get forecasts in real time. If anybody wants to try it, just please let me know. And maybe I'll take the liberty to show a bit how it looks. You can go and see, well, if it goes, see the forecast of different points in Switzerland, and then you can go back in time to see forecast at another time. So that's one thing. And if there is the API, so if you want to try them, just please let me know, and I can give you access to the forecast. Coming back to presentation, last thing I wanted to show, it's preliminary results that we have from a physics-informed graph neural network, where the idea of this physics-informed graph neural network is to take, let's say, images from the cloud index, from satellite images, and based on a graph attention architecture that is constrained with a physical model, with a Vection diffusion model, so that it sort of follows the right path. Let's try to predict a rough estimation of the cloud index images in the future. And now we use the same encoder-decoder architecture, but now this, apart from the past measurements from time series, it receives like the past cloud concentration, let's say samples, the nodes of interest. And also in the decoder, we pass the future cloud concentration at the point of interest, and this produce the future data. So we've seen with this approach, the blue curve, let's say, is the what we call GCLSTM plus pink, and on the green curve is the result from GCLSTM. So we see some improvement from 2 hours to 6 hours ahead, and it's promising. One thing is that this architecture is not fully optimized yet, because what we're doing is we're predicting the future images, and then we put this prediction into the model. Future work, we were trying to optimally fuse the information, really, because right now we just took the model that we had with the model that we created to predict the clouds and blend it. But an end-to-end model would yield a better result, hopefully. So now just to summarize my talk. So just presented Generative, our solution to produce probabilistic forecast. This based on the idea of using a dense network of sensors, like a PV or weather stations. And GNNs are used to model the spatial-temporal relationships of this multi-source data. And most important thing is that the solution is robust to changing in the conditions of the sensor network, thanks to this dynamic graph approach. And also like the inclusion of heterogeneous data sources are good or could help to improve the forecast. One also message is that this approach, I think, more going back to the workshop on minute scale ahead, I think it can be applied to minute scale if you have like enough resolution in time and enough sensor network with some spatial resolution. That could be done. I guess the main problem is access to data, that you have the PV systems on a neighborhood or in a small enough neighborhood that you could have, but the method can prove to catch the ramps. And with that, I conclude my talk. Thank you.
Thank you so much, Rafael. With such an interesting presentation about the graph and these models. Any questions, please? Yes.
Yeah, so I'll just repeat the question. The question was about the relationship between the past window and the forecasting horizon. So we use 6 hours ahead horizon in the prediction and 4 hours in the past. And we started actually looking at 24 hours in the past to have a large enough context. And basically just empirically, we started to try to reduce to see what was enough. And to be honest, even with 2 hours before, it gives enough context. One thing I forgot to mention also, it's that we provide the mean value of the 2 days before, but only like 2 points before to give context of what happened before, but this whole data is reduced. So based on only these 2 values plus the hours of the 2 hours before, it was good enough. We have 4 hours because it's a good trade-off. Also for let's say to catch also a bit more the variability, but having a long context didn't really like improve for this particular architecture. There are other architectures like based on graph attention that actually we use the 24 hours ahead because that's it gives better results.
One more question. Yes.
I thank you for the presentation. So I was curious about your representative nodes. So when you like do the polygons, the topology, is it mostly to make the model training lighter? Because I guess then you put less information directly to the model, or does it also give performance gains?
No, well, first it makes the performance lighter or the computational resources lighter. That's true, but it was more to give robustness to the system, because the quality of data it's serious. So let's say we don't have like an agreement to the system. So what we have is some notes from pvoutput.org that is basically people who want to share their data. So that's why we have so little, but the quality of data it's quite low. And what we've seen also from historical data from other partners, there are a lot of gaps in their data. So first we started on having like an approach of, okay, what happens if we impute the data, if we try to reconstruct the system first and then use that data. But then sometimes nodes could appear or disappear for 2 weeks or a month. So then an approach to just impute the data, that was not really possible. So then that's why we started with this dynamic graph approach. So in that sense, if there is at least one representative node in the cluster, we have data, we are okay, and we train it end to end so that it is tracked.
Thank you.
Did you study the dependency from the number of nodes and the distance that they have to cover all the region?
Yes. We have actually in one of this paper that we published in Applied Energy. We study that dependency. Of course, like the denser the network is, the better results you have. But also there is a dependency on the distance or on the maximum distance. We saw, like, for example, in the outer region, I don't know if I have, the picture here, like in, let's say in Geneva or Lake, on the edges, let's say on the graph, the forecasts are not that good because they don't have full spatial context. They only see or data, let's say, or events coming from one side. They don't see data from full around. And of course, in the particular situation in Switzerland is that it's very dense in the plateau or in the central region of Switzerland. So of course, the forecasts are way better there. And not only in RMSE, because I think like everybody was saying, RMSE is good, you can optimize that, but also they're good, better in shape, let's say, when you do the forecast. In the outer regions in Lugano or Geneva, the forecasts are good on RMSE, but then depending on where the wind comes from, they're not able to catch.
Hi. Also a quick question about the architecture, well, how you make the graph. So I've always wondered with graph neural networks, the dependence on which neighbors you choose for each node. So within the graph, you know, you can have the nearest neighbor, you can have the most correlated neighbor, you can have a neighbor that's 10, 20, 800 kilometers away. And the further away, the more information you get, right, from further away.
Further, yes.
And so how did you choose your neighbors in this graph?
Well, there are two approaches. Like in this particular architecture with the GCLSTM, the graph was actually chosen just nearest neighbor graph. So we use like a 10 nearest neighbor. So it's only based on distance. So the graph is basically representing the topology. And the graph convolution in the LSTMs, what it does is just passes around the information from local node and diffuse it to all the nodes. And well, I think that also has an impact, to come into question of Amadi, that on the length of the sequence or the processing sequence in the past before. So you need to have long enough sequence to be able to process or to diffuse the information across. However, there are other architectures, this other paper that we published in Applied Energy, that are based on graph attention networks. In those kind of networks, you learn a function to predict the connections based on data. So, for example, if you have a sunny day or a cloudy day, it might choose different nodes depending on the data. So it learns from the context, and then it uses that graph to diffuse the information.
Okay, but like a quick change in this one could be to connect one node to immediately to nodes further away, right? To propagate the data.
Quicker. I think that depends a lot on the lead time that you might forecast. So I think if you want to forecast, let's say 2 to 3 hours or 4 hours, that could help because then you can see catches. But how this particular architecture is done, it does that implicitly by diffusing the information across the graph. Because remember that you have this message passing on all nodes at the same time, and then in the next processing time, let's say, of the RNN is basically recursive. So then it will diffuse in time quickly, maybe like in 2 or 3 time steps is diffusing the information across all network. But you're right. For this we created the graph attention network, and actually we have one head, let's say, per window of time in the prediction horizon, because the selection of nodes is different.
Cool. Okay, thank you so much.
Thank you a lot, Rafael, once more. Our next speaker is, Erling Eriksen. We'll give some time to Erling to prepare himself. I would like to give you a tip. The people that are developing neural networks are quite aware about the problems that they have, the problem that they face here. So it is quite interesting that the next generation of neural networks, it is supposed to include also the physics law, or the inputs that we use in our physics models in order to give better results. And this is a good tip because it will be possible in some years to have some kind of personalized use case networks, not just for this case, for our testbed at Patras or at PSA or etc., with all the information needed and not just LSTM or GN graph neural networks. So you're ready.
Yes.
Thank you so much. Please.
Hi, it's a pleasure to be here, and I'll be presenting some work that we've been doing at IFE recently regarding minute scale forecasting from sky cameras, and especially regarding feature extraction in high latitudes. This is motivated by, as other people have explained better than me, the usefulness of predicting solar variability, and especially by the unique cloud conditions in high latitudes with very complex multi-layered clouds. And there are many data-driven architectures that we can use to forecast irradiance, but what makes one work and one not is not always so clear and interpretable. And so investigating one part of this process is the compression of data from when we take images, then we have millions and millions of numbers, and then we compress them down to a single value, GHR or CSI. So how we do this compression can tell us a lot about the models we're using and the systems that we're investigating. So I'll go a little into the data and the setup, show you the methods that I've applied, and present some preliminary results. At IFE, we have 2 sky cameras positioned 1.2 kilometers apart. They take a picture every 10 seconds, and then we have used a reference cell as our target. We have 1 year of data, but for the exploration of preliminary models, we use a single day. Here is a figure diagram showing our feature extraction architecture. So there are 3 options we are investigating, and so we take the raw RGB images and then feed them to convolutional neural network, our option A. We do feature engineering to extract masks of different things that are physical in nature and might help the model. And then we either feed these masks to a convolutional neural network, or we aggregate the data into time series. We then take either of these options and give them to a temporal model to try to predict the GHI. We stack these features with historical GHI, so it's an autocorrelated model. So for our feature extraction, we pre-process our images by correcting for orientation and also the geometry of the equidistant fisheye lens. We resample to lower the data size, and then we extract our features. We extract cloud base height, which is pixel-wise, using the stereoscopic vision of the 2 cameras. We segment the image into cloud and sky, and we extract the cloud movement vector. We also give the model a mask of the position of the sun. For our predictive models, we use a hybrid structure. We either use the LSTM when we have the time series of the aggregated data, or we use a combined CNN LSTM architecture when we have image data. And our reference model is smart persistence. Our models use vector output, and so we predict all the horizons at the same time to investigate the dependence of time effects. As we only use a single day of data for our initial exploration, we have to regularize the model pretty hard to avoid overfitting. So method A, B are structured like this. So we have the CNN, which takes in our image data and then extracts some features. We have a two-layer LSTM network, which extracts temporal features from our historic GHI, and they're then concatenated and input into a last LSTM layer, which makes our temporal prediction. For our method using aggregated data, we take the mean or an equivalent measure from the different masks, and then we give it a look back and then feed it to a two-layer LSTM. So some preliminary results. Here you can see some features that are extracted for a single day. It is unlikely that from a single day you can train a very successful and generalizable deep learning network, but you can gain information about both the model and system that can inform further development, hopefully. And you can also see that we have some spikes in both our cloud motion vector and also in the cloudiness denoted by sigma. And that is from the local fauna at the campus. And so we have both beetles, spiders, and birds that like to hang out on the sky camera, likely due to the ventilator and the warm air is the leading hypothesis. And so the day we chose is a day with a lot of variability, since that's the thing we're interested in, how these features can correlate or give the model any information about the variability. So here is the metrics for the model that was trained on aggregated data fed to an LSTM. So on our y-axis, we have our different horizons, and along the top, we have our different features. And so we can see that it has a positive skill score for most of the period, but for horizons below 90 seconds, it's very negative. And here I've capped the color bar at minus 0.3 to save myself from the embarrassment. And for the normalized RMSE, we can see that not all features have this contribute to the model. We can see that the cloud-based height, for instance, which might carry information about the cloud type, does not really perform very well, which is the second plot here. And the third plot shows the change in RMSE when you take a completely autoregressive model. So only GHI to GHI, and then you give it one of these other features. And so we can see that some of the features give a positive impact, but that it's quite varying and not very large, and that the cloud segmentation of the all sky imager that's placed closest to the reference cell is the only feature that gives a positive impact for all horizons. We can also see that the features that are extracted from the sky merge that's closest always give a better performance than the one that's further away. So the spatial correlation is present. For the extraction that's done by the CNN, here we can see that there's overall a higher skill score, but there's more variability. We can also see that actually when the model just receives the raw RGB images is when it performs the best overall, but mostly on the mid-length horizons. we can see that the cloud motion vector improves the score in the very short term, but is still outcompeted by the smart persistence. So doesn't really, not sure. It shows that some information about the very short term is communicated through this feature. So looking at a few actual forecasts, here we have the LSTM which has gained the aggregated data of the cloud feature. On the y-axis is our GHI, and along the x-axis is our time. The bottom plot shows the error. And so this is basically a smooth persistence curve, which also contains some bias. So if we add our cloud motion vector feature to this, it performs quite similarly, only with an offset. But if we add our forecasts with features extracted from the RGB, we can see that it departs further from the persistence and smoothing and gives a better forecast. And if we use the features from the map of the cloud segmentation, this is the one that performs the best. But as you can see in the bottom plot, it is most evident in the areas where there's a certain amount of stability. So when it changes quickly, then they're all basically the same. But if there are areas of stability, the one that has the cloud segmentation is better at finding the baseline. So if we look at a 5-minute horizon, we can see much of the same. We can see that the one that receives the cloud motion vector, the wind, or the LSTM, performs poorly. It becomes a smooth autoregressive model, while the one that receives the cloud segmentation and has the CNN structure to allow it to extract spatial features is better able to follow the general bias of the forecast. And the RGB model is the one that departs the furthest from the persistence. For a 1-minute horizon, so very short, here the wind, the cloud motion vector is the most valuable feature and produces the best model. And so this communicates that some information about the movement is helpful, which is intuitive. So some conclusions. So it's 1 day of data, so big grain of salt. But there are some things we can learn from how these models extract features. So the aggregated features, they lose the spatial component of the features, which at least with in this scope, it means that it isn't able to generalize or predict at all, and it falls back to this behavior that Yann described before, often when you optimize for the RMSE, which is this smoothed, flattened persistence. And so the raw images put into a CNN, they give the model a lot of flexibility to extract its own features and find out what is important. But it also has a tendency to, because it's more flexible, it's easier to overfit, and it also loses interpretability. Like you can look at the weights and draw some conclusions that it finds edges or highlights, but really what the machine is thinking is lost in the process. And so with the engineered features, we gain some interpretability. We can see that for stable periods, it gains more use from cloud segmentation, and from it performs better with sharp changes when it has the cloud motion vector. We can also see that sub-minute horizons are very hard to beat persistence. even when you feed it a historical GHI. And persistence in this timescale is a very solid assumption. Like if things are going to change in 10 seconds, probably not, is probably true. I think that is all. Thank you for your attention.
Thank you so much, Erling. I saw at least one question popping up from the audience, which is online. So.
Yes. So for training the features or for training the models, I use an autoregressive model, and then I give it one feature at a time. So I look at the effect of one feature on the model one by one. And then Jorge.
Did you also try like a combination between them?
I tried some combinations, like for example the cloud segmentation and the solar position, but the series of combinations quickly gets out of hand, and so I thought it better to present a cross-section of the features to look at the value of each individual one as it's added. Although it's likely that there are compound features that can be extracted when you add these in tandem.
Thank you. Also, for your last conclusion, you said like there is no model that can beat the persistence model.
Oh no, there are definitely models that can beat the persistence model, I think. But I think it's hard when you do, especially with these neural networks, because almost all the fitting you do will be to noise.
And this is happen over all the weather scenarios like sunny, cloudy, overcast.
Yeah, so for the exploration, I used a single day, and that was very partially cloudy with a lot of variability. So yeah, but for 10 seconds ahead, yeah.
Okay. Thank you very much.
Hey, one thing that struck me a bit odd is you mentioned, I think 2 times, how the stable periods during the day was well predicted by the model that used cloud segmentation. Could you comment on that a bit? Because to me, a stable period would mean either continuously overcast or continuously clear view to the sun. So what is the cloud segmentation information actually providing?
So stable periods in this case are much shorter. So just like an area where it's not really going sharply up or down. Also, since we're using a recurrent neural network structure, then the cloud segmentation also contains information about the change in cloud segmentation, so that when you give it the cloud segmentation, it also has information about how that changes over time. So if there's a period where the cloud segmentation doesn't change much at all, that can be an indicator to the model that the GHI won't either.
Thank you.
Great. That's all. Thank you so much, Erling. Our next speaker is Angela Meyer for TU Delft.
I need my own adapter. I need my own adapter. Oh,
You don't have anything.
yeah.
Is this okay, I think?
But I need to be there.
Are you sure it's not working like this? Because I think that it's as Michael, it's the Meyer as well. So this one's no, it's you've been listening from that one.
And I just need to share the screen.
Hmm? Try to upload the presentation. Is that one? No? Okay.
Good.
Maybe I put it also on the screen.
Thank you so much. Good. So, so our work is this work that I'm presenting is mainly motivated by the goal to estimate solar radiation. So let's call this global radiation GHI or SSI, surface solar irradiance. Now we're speaking about global radiation, but it could also be in principle done for other components. So this work is motivated by estimating global radiation in near real time from satellite data for spatially extended areas, and also for forecasting this, right? So we don't look into we are using satellite data. We're not using any sky camera, sky images, or any like local area. We look at regional scales. We are interested in regional scales, and one of the reasons is that for one of the projects that we look into, people, this is going to. We have one company who we collaborate with who is interested in trading. Okay, so I should also say, me myself, I'm based in Bern, Bern University of Applied Sciences and the TU Delft. And this work that I'm presenting here, it's the most important point, is heavily has been done by, or is being done by two of my PhD students, Kevin Schurman and Alberto Carpentieri, and we are funded by the Swiss National Science Foundation and InnoSwiss. You can see these two students, PhD students, who are not here today, unfortunately, in the upper left corner and lower right corner. I seem to not. Can you see them? Yeah. So this is Alberto Carpentieri, who has contributed heavily to the forecasting, and this is Kevin Schurman, who is now working on an emulator model for CERA-3. So I'll start first with the emulator and then go on to the regional solar nowcasting. And all of this, just see this as like a trailer basically for what, I mean, this is, both parts will be presented at EGU next week in more detail if you're interested, by both PhD students. Okay, so first of all, the first part is we are looking into emulating CERA-3. I think this fits pretty nicely to this workshop because what we try to do is to do this basically to estimate global radiation in, well, real time, and in the sense that as soon as the data become available, like the level 1 data from Meteosat, second and then third generation at some point, become available through EUMETSAT. What we have seen so far is that previous emulation methods. And I should say we're not obsessed with CERA-3. It's just that we needed some, let's say, some ground truth, and CERA-3 is a not very good data set, and it's publicly available in contrast to some other data sets. So that's why we use it, but there's no reason why this should. I mean, this would work as well with other data sets. Good. So existing methods, what they do is they so that there have been a couple of papers already on studies on basically emulating estimating, like deep learning models that estimate global radiation in near real time, but they are using let's say point estimates only, and they are trained and validated with parameters. And our explicit goal was to have kind of spatially extended estimates. So we directly estimate the solar radiation from a Meteosat level 1. As I said, we're using CERA-3 as ground truth. And in addition, we are now working on, or Kevin is now working on fine-tuning this the estimates that we get on parameters, which gives pretty nice results. Good. So let's maybe maybe I spare you these slides on how we estimate solar radiation. Just briefly, we have Meteosat there, geostationary. We have an image every 15 or even 5 minutes in infrared and visible bands, right? So this is Switzerland again, which you've seen before. This chart, and what that's kind of one of the images that we want to get at in the end, a map, spatially extended map of global radiation. So yeah, there's a lot of processes that you can now go and model with using radiative transfer modeling. That's basically physics-based modeling, and you have all of these different spectral bands basically. But we have this is just basically the background. You can see the spectral bands from Meteosat that we're using. One aspect that we are paying, I mean, this project only started a couple of months ago, end of last year. So one aspect that we are going to pay attention to a lot is generalizability. So what we have seen, and then also others have reported this, is that you can your model can be biased basically based on the data sets that you're using. For example, if you're only training on parameter data from some country, let's say from Germany or north of Europe, then you have only certain types of albedos in there, and your model will, we have seen that will not generalize so well if it's just trained basically on subsets like not representative surface albedos, will not generalize so well to, let's say, more southern regions where the albedo tends to be look a bit differently. Okay, so some details, what we did for, what we are currently doing, or what Kevin is currently doing for training. We use 5 years of data for training the model and 1 year for validation. We do have, then in addition also, we're doing the validation actually with parameter data. So we have BSIN stations and then also parameters from the German Weather Service and KNMI, and the most important reason for this is that they have a nice API and a good open source data quality, data policy, unlike unfortunately some other weather services. So that's the architecture. I will not go into any detail. That's what we started with. You can see the different Meteosat channels, images of those channels in the upper left corner. And then we are running convolution operators. We are also using additional features. That's of course pretty important. You need to also provide, for example, the time of year and time of day, right? Because if you also have, if you have physics-based like model or algorithm that's 0.3, they also compute, of course, first of all the field radiation, and they need to have that sort of information about the azimuth angle and so on as well. So we also need that, of course. We also input the latitude and longitude and so on. Good. First results, and as I said, I am not going into any technical details. If you're interested, next week is EGU, and this will be presented on Thursday. So this is first the results. On the left-hand side, you can see the emulator, and on the right-hand side, you can see Sarah 3, and then the left, the rightmost plot is this one here is the difference between them. And this is basically just the first attempt, which I think looks relatively promising. In terms of, I was actually quite astonished when I saw this for the first time, how well this emulation works. We now, this is the data that we're using for, on the one hand, validating the model, but then also fine-tuning it to different regions. So as I mentioned, this is German Weather Service and Dutch Weather Service parameters, and then also a beautiful data set provided by actually the PVPS data set, which very nicely also provides us data from North African parameters. So these are just first results. I mean, it's not published yet, it's preliminary first results. You can see Sarah 3 on the left-hand side, the root mean square error, and with regard to those BSN station or PVPS stations, which are comprise also BSN stations. And then on the right hand side, you can see the emulator, and you can see just by comparing the colors basically that the magnitudes are pretty similar. It works astonishingly well in that sense. We also looked into fine-tuning, so basically adapting this model to more specific locations, let's say. And you can see here, maybe just look at the upper right plot. You can see here the root mean square error of the SARA3 global radiation with respect to the DWD stations. And then this is the box plot for the distribution of the emulator, basically, that with regard to the DWD stations. And then on the right hand side, you can see the accuracy of like the distribution of the root mean square errors of the global radiation that you can achieve if you with fine-tuning, with additional fine-tuning of the model on subsets of those parameters from for in this case Germany. And we saw, I mean, the fine-tuning also gives good results for other regions. Good. Then one interesting side note, I'm based also in Switzerland, and you have seen a figure from Switzerland before, so maybe I start with this one. So this is a study we did 2 years ago, and in exchange also with SARA2 team at the time, with Jörg Trennmann. And we kind of, this was just we used this dense ground network of 130 Swiss parameters, like very nice network operated by the Swiss Weather Service. We used that to validate SARA2 at the time, and also another data set, Heliumont, by the Swiss Weather Service. We found large biases, basically. So here, these are the biases, and this is the uncertainty. And the important thing is the altitude, right? So we looked basically at this, at the effect of the altitude, and we clearly saw problems with, you can see, problems for this discriminating snow versus clouds, basically, right? And especially, oops, it's going automatic. If for SARA2. And now, so it was really curious to see what does that look like in SARA3. You can see this, I mean, the root mean square error, at least on the right-hand side. And so first message from the slide is there are still issues. At least that's what we see in our preliminary results. We'll look into this further. And on the right-hand side, that's quite interesting. Oh, I mean, in the end, not surprising. The emulator basically comes up with the same or very similar. It just emulates SARA3, right? So we see also these biases so far in the emulator, and but we're confident that we may, about how to get rid of those biases or how to reduce them. Good. Now, to not keep you from the coffee break for too long, I'll just very briefly go through the second part of this presentation, which is on regional nowcasting. So once we have estimated the global radiation in, let's say, near real time from the Meteosat, we would like to also forecast, right? That's at time scales of up to a couple of hours. So we have presented, just briefly presenting two models that we have proposed. One is in the last 1 or 2 years. One is an autoregressive model that is basically, I'll show you in a minute. So and the second one is a generative model, and both of them forecast regionally spatially extended global radiation fields. Right, so just a brief overview of how the first one, we call the solar steps, because it makes use of a library that is traditionally being used, or that is being used for precipitation nowcasting, right? So we have applied this, adopted this for a cloudiness forecast, basically. So you have a series of maps here, also of images, basically, of cloudiness. And then you have an optical flow model also, and then you can basically add get probabilistic forecasts of how much PV is being produced in a region once, if you know how the PV is distributed in that region. Okay, so in a nutshell, what this first model does, and you can see the publication below there if you're interested, is it is a spatially extended probabilistic optical flow model that acts on Meteosat derived global radiation. So that still works on level 2 data, but we're now extending this and getting good results to run this on level 1 data. It mimics the time evolution of the clear sky index, and it makes use of the fact that this time evolution basically depends on the spatial scale. So I'll show you in a minute what this means. So we are having basically one autoregressive model for each spatial scale that we that we identify, and that is what contributes to the good performance. And we see a 10% reduction in CRPS with respect to just a pure probabilistic optical flow interaction model. So here's what I mean by we have, and I should say this is the work of my PhD student Alberto Carpentieri. I just present on behalf of him. So here you can see what I mean by spatial scales. This is again a map of Switzerland, clear sky index over Switzerland, and you can basically decompose this map and also find the optimal number of decompositions, like spatially decomposes with a Fourier decomposition into different coarser scales and finer scales, and then model these scales separately without regressive models. That's basically where the performance improvement comes from. Good. Okay, so this is an idea. You get the images here. They're transformed into level 2 fields of SSR, GHI, or clear sky index, and then we decompose them in the spatial fields. We compute the cloud motion vector fields, and we have different autoregressive models that then capture the fact that larger cloud patches, basically, they evolve differently over time than they have different autoregressive behavior than smaller structures. And here's just an animation where you see how the forecasts work. Good. Now, last 3 minutes or 4 minutes, and then I'm happy to take questions and go for the coffee with you. So we also proposed recently a generative model. So the diffusion model, you can see it is pretty, relatively complex architecture. I'll not go into details. If you're interested, you can see more technical presentation about this model on Monday at EGU in Vienna. So what we do is we have these images again of clear sky index level 2 data derived from Meteosat. We then encode them, so we kind of condense them in a sense in a latent space. We do the nowcasting in a latent space, and then we have a diffusion model basically here for that mimics the evolution of the cloud. So that's kind of like the stochastic part that is being modeled. You can, so one nice and then you can look this up. It's also published on the archive and now in review. One nice feature of this model is that it can adapt to cloud brightening and darkening. So if you're, if the region that you look at becomes darker, let's say, like you have more clouds coming, or the clouds you have more rain clouds coming, so the color effectively of the clouds changes, then this model can mimic this. You can see this here. This is PDFs of the clear sky index, how it evolves over time. Another nice aspect is that this new model, which we call Shapecast, increases the sharpness of the forecast, but at the same time it maintains the coverage basically, so the reliability. And last not least, we also prevent an effect that has, I think, also been mentioned previously, that is blurring with increasing lead time. So these generative models have the advantage that you don't get blurred out images as time evolves, forecast time evolves. Good. So in summary, last slide. What I presented to you is that first of all an emulator that's basically a deep learning model that estimates spatially extended global radiation from Meteosat level 1 data. We find in our preliminary results so far that the mean square error and biases are relatively equivalent with Sarah-3 at least. The model would, I'm confident to say that, would also work with other products, is not specific to Sarah-3. The latency, so the model, once it's trained, I mean, training it costs some time, but once it's trained, it runs in just a few seconds. And then you can also use parameters to fine tune it even more. The second part was a regional solar, or two actually regional solar nowcast models that outperform with the state of the art, which is probabilistic advection models. They spatially extended. One model was autoregressive basically, and the other one was a generative model that avoids blurring and adapts to brightening and darkening of clouds. Thank you so much.
Thank you so much, Angela. There is one question from the audience here. However, I would like you to check first the questions from the audience attending online. There is some comments in the chat.
Let me see.
Is there any question for you?
Somehow I can't click here. Let's just see.
Yeah.
Sorry.
Yeah.
Is this for me or should I think it's not for me. No.
No. Yeah, we missed that one. Okay. So, Sylvain.
Hello, thank you for your presentation. It was very nice. I have a whole question I will re-ask today about Sarah-3 emulation. As a Sarah-3 is a scheme basically made on visible channels, does it worth to use all the MSG channel to get these results? Maybe if you use only the two visible channels, do you think you will have the same results?
So you ask, sorry, I don't need to repeat the question. Yeah, I mean, we could just use only the same channels that Sarah-3 has been. Frankly, we did not bother to try to redo what Sarah-3 has been doing and just using those channels. But one of the things that's obviously we're going to do next is to look into which channels are the most important ones and can we reduce that model even further. I mean, there are nowadays good ways to do that with feature importance and so on. So we see that, of course, the visible channels are quite important, and but we'll just basically do that in a data-driven manner. So that's what one of the things that Kevin is working on currently to see which channels are most important and quantify this, and also how does that depend on time of day and the region we're in and the albedo and so on, and then try and see whether we can reduce the model, for example.
Okay, thank you.
Thanks. Is there anything else? No. So a big applause for all speakers. Thank you so much. Please be back in 15 minutes because you need to check also data-driven for wind.
Yes.
Yes, perfect.
Yes.
Okay, good. So I guess it's good morning, right? In Copenhagen now. Good morning, everyone. So my name is Jie Yan from North China Electric Power University. My topic today is AI-based weather prediction for the wind power forecasting. So it will be mainly on the wind prediction. And yes, so we all know that this wind speed prediction, wind direction prediction is very, very important for every scale of the power forecasting. Not only because of the accuracy here. Because it's a cubic relationship between the speed to the power. So when the wind power share in the power grid is increasing very fast, so the accuracy required for the wind power focusing is also increased very rapidly. You can see from the policy from the power grid, every year they would increase the requirements for the power focusing accuracy. But also we would find two challenges or two main requirements for the power focusing and also to the weather prediction. The first one is we hope to have higher resolution for the weather prediction. Now we mostly use this 1 hour resolution, and then to use some way to downscale it to 15 minute resolution and use it to do the wind power focusing. But we could see from this figure that the brown color curves represents the NWP data, which you can see different curves represents different sites, different locations. Here is one wind farm, several wind farm here. You can see it's every curve seems very high correlated for the NWP data. But in fact, the real situation is those green curves here. In fact, the real measurement wind speed is very diverse correlations. So you could see the difference from the NWP and also the measurement data. So you lose some of the fluctuation of the in the time scale. I mean, lost some of the fluctuation for the real measurement wind speed, but also for the spatial scale, you could see the correlation for the NWP is too high, much higher than the real situation. So this is we hope to do something about it. And also now the new policy from the Chinese power system, the focus horizon is raised from 1 day, 3 days ahead to 10 days ahead, and also with resolution of 5 minutes. In some province, the time horizon for the focused requirement is extended to almost 1 month. So it is not into the national standards, but in some province, the power grid has already launched such policy to request a longer focus horizon. So what we hope to do is how to solve this problem about the accuracy, high resolution, and even longer focus horizon. AI weather prediction is a new and very hot frontiers. Hoping to solve the challenges for those above problems. And now we could see like Pangu and Fengwu and many Fuxi, many large-scale weather prediction model have been launched and published and even tested in different institutions and departments. Even I think it will be in the this year we just have one very a great workshop about the AI weather prediction. So there are many information about how the AI algorithms are contributing their learning ability to the weather prediction field. And we also do something about the AI-based weather prediction and kind of from different perspectives. in different ways. I mean, the first one is just a 3D, use a 3D conventional neural network model, which is very simple, but the basic idea, we hope to build up the mapping the relationship between the global focused field and the wind measurement data within the wind farm. So you could see that the basic, to my understanding, I'm not an expert on the numerical weather prediction. To my understanding is the numerical model is hoping to build up like from the global scale to the regional scale. But when you do if you hope to do even higher resolution, which is very challenging, but here we hope to build up a model, an AI model from the global scale to directly to the wind turbine level. Using the 3D CNN model and also considering the topography information into the model, and we tested in the Mongolia province, and I will show you the detail about these 10 wind farms, very large area, the test result here. And this is you can see we published this paper in the journal, so even a little bit earlier than the other one. But yeah, I have to admit this is a simple model and just be tested in one region of in China. And here the accuracy is not that much very better than the performance of NWP, but you could see they have two advantages. So generally the accuracy is slightly higher than the numerical weather prediction result, which is the average result for 10 wind farms, and in total there are 20 NWP sites. And also you could see for the fluctuation, the real from the time resolution, the time scale, the fluctuation can be better fit than the NWP one, which can show the higher resolution for the time scale here. So, and then but after that, we then to discuss a problem, we consider, yes, now there are many researchers who do the NWP correction using the measurement data to help to improve the accuracy and the resolution of the raw NWP data. You could see many papers and reports, and even for us, we use many of the AI algorithms to do that, to mapping the NWP directly to the measurement data. But now if you are using this AWP one, that is what is our AWP means AI-based weather prediction. We name as that. You already use the, at the very first step, you use the measurement data into this data-driven model, but how will be the result if you use the measurement data again to do the correction again, which means, so that will be like NWP plus correction, and versus the AWP and the correction. So the results showed even we already have used those real measurement data in the AWP model. When you use those data to do the fitting, to do the correction again, it will also further increase the accuracy by nearly 1 meter per second on average. So that will be very how to say, inspired us or give us confidence. So first of all, when you use the real measurement data, you could use it to fully advantages. So it will also means that for the AWP, for this very simple AWP model, the 3D-dimensional CNN model, it still leaves some space for us to further improve for the data, to dig the data value. So to this end, when then to use even a more complex model to try to do it, and also extend the focus horizon to 40 hours ahead. And here we have three technical route here. So the first one is nearly the same as the first one. Just use more complex model as the multi-scale CNN model, also to mapping the global field to the wind measurement in wind farm. And the second one is just a purely time series data driven, like informer, transformer things, do the very long time series data to do the prediction, and then to combine them all as is the be more like the ensemble method to do this, to combine these two results together and to generate a new one. And then we tested this result in northern part of China. There are totally 10 wind farms and spread like this. The range of this region will be like 300 kilometers, multiplied nearly 300 kilometers. And then there for each wind farm there are one or two or three NWP sites. It depends on how large of this wind farm. If one wind farm is very large, then and also not that much flight topography, will also consider the topography. There are different source of NWP and also different sites of the NWP in one wind farm. So in total, there are 20 sites for the NWP, and for each site, there are 3 sources of NWP for comparison. And the total time period for the data is from 2019 to 2020, 2 years in total. And for this NWP data is 1 hour resolution. And here shows the general error results. Here you can see for these 3 sources of NWP data, and also the AWP, our proposed AWP data. You could see that for the average error is relatively nearly the same conclusion length. The accuracy is not largely improved than the best NWP one, but it still improved a lot than the other 2. I should mention that these 3 sources of NWP is very widely used in many provinces in China. So these 3 are representing the high level good performance in China. So we selected these 3. And but you could see even for this one, the average error is nearly the same, but the uncertainty range of this and maximum error is slightly lower than that. So you could see there are for different perspectives, the AWP results kind of give us confidence to further to show a good performance from many perspectives. And if you here is an average result. If you see the individual 20 sites, individual sites, you could see the color represents the multitude of the altitude of the arrow, and the darker the color and the larger the arrow. So you could see generally from this side. So for most of the sites, the AWP arrows is lower than the others. And also that it is the same similar conclusion that from the fluctuation for the time scale resolution, AWP data is better than the original NWP, which you could see they can show the real fluctuation more, or fit the real fluctuation better than the NWP data. So this is 3 days, and this is a long how many days is 1 hour is 200 hours. And also here is nearly the same. You could see different sites shows different similar results. And also that you could see they could depicting the spatial characteristic, the correlation, the real show the real correlation. They predicted the spatial correlation more accurate than the NWP. So this is the 3 sorts of weather prediction results, and this green interval, this green color, shallow one, means the real interval fluctuated for this 20 site, and the red color, the brown one, green one, purple one. So this interval represents the interval shows by the NWP, the weather prediction results for these 20 sites. So you could see from this picture here, the gray color, the gray range is very wide, which means that in these 20 sites, the real wind has a very diverse correlation, not very high, because of its, the topography is relatively flat, relatively complex. But you could see here that for the NWP data, so the 20 on this 20 sites, the correlation is very similar to each other, which you could see from here. The range is very narrow. So for the AWP is not that much, accurate, perfectly fit the range of the real situation, but is wider than the other NWP, which means that you could show the spatial characteristic of the real wind much accurately than the others. And in the third one is how to extend the NWP data extension from 1 or 3 or 7 days to even longer days. We just this is not a purely AI-based model. We also use the NWP data, 1 to 5 day NWP data, and 6 to 10 days NWP data, and use the AI model, AI algorithms to try to merge these 2 kind of NWP and the real wind measurement data to generate the extended horizon result. And you could see from here the black one is the original NWP data, and after the correction, after the model here showed here, you could see they decrease the error largely. And in different months and in different wind speed ranges, is you could see shows nearly the same result. The correct one is this dark blue color, and the original, the shallow yellow color means the original 10-day ahead NWP, which has very high errors generally, but after the correction, after the AI correction, you could see they reduce the error very largely. Here is also, I think it's we test this model in another provinces for also like five or seven wind farms, and they also try to use it into the solar plant. Solar plant, power plant is nearly the similar results, the similar conclusion as this. Yes, the conclusion. We hope to use purely the AI algorithms to try to help us to improve the weather prediction from three perspectives. They help to improve the accuracy, to improve the resolution, and extend the focus horizon. And we try different model, try different technical route, like we mapping the global field to the wind measurement data. We tried purely informal time series data to time series prediction method to do it, and also try how to assemble it, how to combine it, them together to generate a new weather prediction result, and also try to how to use the AI algorithms to extend the focus horizon. So the results show is promising, although the average error is not that much higher than the NWP data, but it still shows many advantages, good features for us. And yes, I think it's very promising to do further on this. Try to improve the overall accuracy, and also try to. I would say that in the above test, we use the measurement data for the 1 hour and 15 minutes resolution. But if we could use them we could use even higher resolution, the measurement data, like 1 minute or even higher. And I believe they will still leave many, I'm still confident to use to have even higher resolution prediction, like the minutes or minutes resolution or second resolution. Okay, thank you. That's all.
Thank you very much. I hope you could hear the applause. And since I'm looking at a lot of hungry faces at the moment, we should limit ourselves to 2 questions, maybe 1 question here from the audience, and you could choose 1 question from the chat. Is this okay?
Okay, no problem.
Is there someone with a question here?
Wind farm is this one maybe.
Can you repeat the question also from the chat, because we cannot see it at the moment?
Yeah. Which one is for me? Wind farm effects on the atmosphere included in the NWP models that you use for comparison. Yes, I think so. It must be. I should say, one of their I used the 3 NWP model. I think there is one source is from EC. So you know the European NWP data is also very popular and is also received many good results in China. So I believe. So the wind farm owner doesn't tell me which one is which, but they told me that they also use the EC one, so it must be one in these three. So I think he considered the atmosphere, wind farm effects on the atmosphere. I'm not an expert on that, but I think so. They claim they, and the other one is from one Chinese company, and they claim that they based on the NWP and do the wind farm effects into their model, and then to generate a new results. So I think at least the one source of NWP are considered wind farm effects. Is that I hope
Thank you very much.
Yeah.
I think if we
Okay.
have more questions,
okay, EC doesn't include.
address you
Okay.
directly. Perfect. Thank you.
Okay, thank you.
So now we come to our last speaker for this session, and this is Janna.
Just give me a second to share my screen. Can we get rid of this flag at the bottom? Is it possible? No, not the talking one, but the, yeah, okay. Then there's a okay. Yeah. Yeah, thank you for the short introduction. Okay, I try to keep myself short. So I'm a PhD student at the KfW University of Oldenburg, and we are part of the Wind Research Center. And today I'll present some parts of our results from the WindRAM project. And I want to just shortly state in the beginning that the minute scale power forecasting, or the lidar-based minute scale for power forecasting, was developed by my former colleague Frauke Theuer, and the ramp evaluation, or the ramp event evaluation, was done in a master thesis by Juan Gomez-Sanzola. Yeah, but I think we already had a nice introduction from Robin into LiDAR, so we can start right in. And also this motivation slide is, I think, also known for everyone here. So what can we use our minute scale power forecasting for? Of course, for balancing, economic balancing, and wind farm and wind turbine control. But we are mostly focusing on the economic balancing here. And okay, why are ramp events of interest? I mean, I think that's also mostly clear for everyone, but just from the offshore wind side, maybe to just mention it again, of course, we have a high density of wind farms, for example, in the North Sea, and if you then expect a ramp event to happen, that can cause, of course, strong gradients in the feed-in of the grid. And in general, these ramps, we all know, are hard to predict, and statistical methods have their shortcomings here. And we try to improve it with the LiDAR-based forecast. And on the right-hand side, I just brought an example plot of some of ramps we saw in the data. So in blue, you will always see the ramp down events, and in green, the ramp up events. And yeah, just as a start. And to give you a brief introduction into the LiDAR-based power forecasting, we already heard from Robin. There's a scanning method which is called PPI, so Plant Position Indicator scans, and these we performed as well. So we have a fixed elevation, so we try to scan horizontally, and so the elevation was mostly zero, and then we changed our azimuth, so we have an opening angle of something like 100 degrees and stuff, but I will get to that on the next slide. But then we had this area of measurement points, as you can see on the right-hand side in this example plot. And for each measurement point, we then use the Lagrangian advection. So each point or each vector has its local wind speed and wind direction. And then we propagated this in time. And just to simulate this shortly, I've plotted here some wind vectors and an example wind turbine here in red, and the area of influence we consider for that specific wind turbine. And if the wind vectors reach this area of influence, when they are propagated, then they will be accounted for the prediction of the power of that wind turbine. So just to simulate it, depending on their direction, wind speed, yeah, okay, it was a bit lagging, but yeah, they are propagated, and yeah, for example, then we would have in this case 3 vectors considered for this wind turbine. And this is then also visualized, or if we then reconstruct basically this propagation, or if we visualize, if you now have a look again at the graph, I hope this video works, then we will end up with something like this. So performing these scans, yeah, just continuously, and yeah, just this as an introduction to the method. And now just where did we, so the wind farm project, we measured or we performed measurements in the wind farm Nordergrunde. It's a very small wind farm just north of the Jadebeid, and it consists of 18 wind turbines and has a total power of 110 megawatt. And there's also an example LiDAR scan indicated there. There was not only one LiDAR, but also a second one. But let's first have a look at just the layout of the wind farm. So the wind turbine at the very bottom, marked in red, that was the wind turbine where our LiDAR was installed for the forecasting measurements. And just for the people who are interested in the LiDAR details, it was a WindCube 400S. For this result I will present on the next slides, we analyzed 1 year of measurement. And as I said in the beginning, we used plant position indicator scans horizontally measured, and we had the measurement distance, so the range gates were from 300 meters up to 14 kilometers, and we had an opening angle of 110 to 20 degrees, and it took us 1 minute to measure this these 120 degrees, and we had about like 6 seconds set back to the beginning of the scan. And we, aside from the horizontal PPI scans, we also used some multi-elevation PPI scans, so changing the elevation of the PPI scans to get information about the atmosphere, so to extract vertical profiles, which we use to get our measurements to the hub height of the wind turbines. And what was also, what's an important point is that we always adjusted our measurements to the wind direction. So automatically the LiDAR was following the wind direction by extracting the wind direction from the scans. And once the deviation was too big, we adjusted it. And yeah, so I think that's what it's regarding the wind farm. And so how did we analyze the wind ramps and the ramp events? So we were lucky to have SCADA data from the wind farm Nordergrunde, and we processed this to have 1 minute averaged 1 minute averages of the power, and we filtered it for the viability of the wind farm. And in the end, we considered the aggregated power of the wind farm because we were interested to look at the feed-in in the grid, or also what the traders would use. And using this data, we then identified the ramps in the SCADA data, and by just defining the ramp, I will tell you more about it on the next slide. And by that, we had masked our data, and with this information, we could then check how our LiDAR-based forecast performed during these ramp events, and we compared it against persistence. So our, sorry, that was two. Our ramp definition, it was like just a, I mean, those who have looked into it know that there's not a real fixed definition of a ramp, so it really depends on the use case. And this is just a start to look into the data. And so we defined a ramp to have a certain power change within a certain time window. And for us, it was like 40% of the maximum power of the wind farm in less than 60 minutes. And to get the power difference, we used the minimum maximum function. So looked for the extreme values within that window, and we used then a rolling window and could that then identify the ramps within the data. And what does it look like? Just to have a closer look at it, again, we have here the power and the wind speed over time. And again, some examples of the ramps identified in the data. There are some limits to this algorithm or to this definition of a ramp. Also, the duration of the ramps in this case, since you detect the same ramp with this rolling window again and again, we just shows here as the first start, the shortest duration of the ramp was chosen. This is why also some ramps are cut off, or also due to the fact that the number of wind turbines operating was set to at least 12 wind turbines. We also, in that case, neglected some cut-in, cut-out situations. Yeah, but as I said, that was just the first start. And just to look at the whole year, we analyzed to look at some characteristics. We'll start with a plot here. So we have the occurrence of ramps per month. We had some months which have a very low occurrence of ramps, but that's mostly also related to the data availability. So this is not really giving you information about the seasonality. So just to make that clear, but we can see, okay, we have, at least in this data set, found more ramps in the winter month. And we have more or less even number of up ramps and down ramps, according to our definition. And the average duration of a ramp was about 45 minutes, but we also had some really short ramps with 5 minutes, and of course reached the maximum possible length, 59 minutes, due to our definition of this window of 60 minutes. And yeah, for the average amplitude, we had like 45%. So you can more or less say we have a bit like close to 1% change per minute for the ramps. And but we also have had some really large ramps with 74%. So these we could also capture. But what we're really interested in is like how we performed with our forecasting during these events. And now we will see some graphs, and we will always have the lidar-based forecast here in red and the persistence as comparison in blue. And we start off with the root mean squared error, and we distinguish between the whole data set, so with the empty boxes, and the filled boxes are then the ramp events. And what we can see for both cases, we have problems in actually predicting the ramps events, but we can already here see that the lidar-based forecast has a lower RMSE than compared to persistence. But to compare them a bit better, we can also have a look at the skill score. I think most of you are familiar with that. And here we can see that actually we outperform persistence nearly up to 20%, at least for forecast horizons. Sorry, I missed it, for forecast horizons from 5 minutes until, yeah, let's say 18. And you can already see that we, for the lidar-based forecast, we have a problem for the larger forecast horizons. I think we can check that out on the next slide a bit closer when we look at the bias. So again, we have in red the lidar-based forecast, in blue the persistence, and now the bias against the forecast horizon. And there we can see we have quite the drop-off for our lidar-based forecast, around like 15 minutes. And this is just caused by the limitation of the measurement. So we have a problem that of the high wind speeds we cannot really capture, at least for the longer forecast horizons. For this, we would need a larger measurement range. And so that's why we are underestimating the power, like due to missing information basically here. And what's really interesting also is to have a closer look at now comparing the ramp up and ramp down events. So there we can see actually in this comparing to persistence. So again, blue is persistence, red is lidar-based forecast, and we can see that persistence is
over or underestimating the ramps just as it detects the ramps too slow. And for us, we with the lidar-based forecast, we perform a bit better. But as we've already seen before, after around 15 minutes, we get to the problem of our systematic underestimation of the forecast due to the limitation of capturing high wind speed. But still, it's really nice to see that actually, at least for forecast horizons up to 15 minutes so far, with this definition right now, we can outperform persistence. And as we've heard already yesterday, so in Germany, we can already use this information now for trading. So that's kind of cool from our point of view. And I now rushed quite through the presentation, but I think that's hopefully fine. And just already coming to the conclusion, so at least with the we always have to keep in mind this result is really depending on our definition of the ramps. So if you change that, you would end up with a different result, at least to some extent. But within this 1 year, we could already identify 364 ramp events. And as I mentioned already, we have an average duration of 45 minutes for a ramp. But we also capture ramps with a change of 74% in power. And we could already see that we can perform better with the lidar-based forecast comparing to persistence. And if you're interested in what comes next, we of course want to check also how now we use the SCADA data to mask our data for ramp or no ramp event. And the next step is of course to detect actually, or to check how good we are in detecting the ramp events with the lidar-based forecast using the ramp definition directly on the forecast of the lidar. And also the definition of ramps needs to be adjusted for the use case. So we are in exchange on that, which definition of ramp is most suitable for example, traders. And then last but not least, we are also looking into improving the lidar-based forecast, of course. So there's more work coming up. We have future up or hopefully starting a new project as well, hopefully with also extended lidar range. And if you're interested in general on the minute scale or lidar-based minute scale power forecasting, there's a paper in the pipeline. Also looking at atmospheric stability differences for the forecast, and that will be published soon. And just to finish up, we of course acknowledge all the parties which helped us to perform these measurements. And I think that's fine so far. And if you're interested in the works, you can check out some references. And with that, I'd just like to thank you for your attention.
Thank you very much. So I've seen there's a big number in the chat. Maybe you can choose the question you like from the chat, and I'm looking if somebody here is either very hungry or has an urgent question.
Yeah. Oh, old, right? Yeah, okay.
Oh, perfect.
Fine.
So I have some Elliot. Yeah, thank you for the presentation. It was great to see you've improved on persistence. Maybe I didn't fully understand the forecast method, like how you're actually producing them. Is it a deterministic forecast you're producing? Did you consider maybe like something more binary, like if the ramp is coming or not, like a clustering technique or some decision tree or something like this?
Not yet so far. So that was really very first start, basically just masking the data, saying, okay, here's the ramp, here's no ramp. But as I said, like we have some shortcomings, of course, but we will look into that in the future to adjust that.
Yeah, you may look at like CRPS or some other, like an event metric for that rather than just RMSE or something like that. But it's good work. Thank you.
Yeah, thank you. Thank you for the input.
You have a déjà vu.
Yeah, so thanks for the really interesting presentation. And I was wondering, how exactly are you getting the zero elevation from the transition piece up to hub height, since that's probably what we are interested in.
Yeah, so okay, so yeah, we are I think I'm sorry I did not even mention that we are located on the transition piece, so we had to account for several issues here. So of course the transition piece is also influenced by the tilt of the wind turbine or the thrust on the wind turbine. So we had some inclination sensors additionally installed on the lidar. So first we adjusted for or corrected a bit for the tilt of the lidar, and then basically we have this vertical profiles, and there's a tendency method. So we more like compare the change in the wind speed from the time we measure to the forecasting time, and then compare the change in the SCADA data. And by that we can basically add a correction factor, and yeah, to account for that. So we do not extrapolate our wind speed measurements to the hub height. That's what we just take the tendency that in the change, but that will be in detail in the paper. So this is like a bit tricky, but we can also talk about it afterwards.
Thanks.
So is there, of course, in the back.
Yeah.
Hi, thank you very much for the presentation. I also enjoyed it quite a lot. And so I was wondering, when you compare to the persistence forecast, was that a comparison of the entire period, or did you filter out periods where the CNR was too low, for instance, or when wind direction was from the farm, so that the lidar would be blocked by the other wind turbines?
No, yeah, this data was already filtered for, like, say, for the scans we can use for the forecasting. So only those we considered valid were then used for the comparison within this 1 year of period, 1 year of measurements. Yeah.
So do you have on the top of your head, do you have an idea roughly on how frequently this would be in a particular situation, or when you could actually use this system? For instance, would it be feasible to have just one LiDAR like this, or would you have for one in each of the 4 directions of the farm?
I can't give you a number right now for this wind farm here, but I can tell you that at least we are planning for the future to have actually more than one LiDAR in a wind farm installed to perform this forecasting. So, and then going for basically the outer corners of the wind farms, and to cover more directions, because, okay, of course we had here like adjusted ourselves. So the campaign was especially designed for the forecasting. So we adjusted ourselves, like, or located the LiDAR so that we can cover most of the main wind direction area, but of course that had shortcomings. So yeah.
Yeah, and that's the most crucial thing is the wind direction, not the sort of quality of the return signal. Yeah. Okay, thanks.
I mean, just maybe to add shortly on that, of course, the shortcomings are a bit if you have some REMs coming with rain or something like that. And that's also what we want to have a closer look at, and how often this happens, and to get some better insight on that.
Okay, perfect. If there's further questions, you can address Janna directly.
Yeah,
with this, I would like to close this session and give over the mic to Gregor.
Yeah, thanks for coming. Thanks for attending. I think this was a fruitful workshop. I've heard a number of good comments here. If you think this was a good workshop, come to me and tell me. If you think this was not so good, go to Yann and tell him. One of the things I was responsible for was first of all lunch, where we're going now. It's the same as yesterday, where we're just getting the food and don't have to pay. And the other thing that I organized is that we get our photo taken. Looking at the weather, it's probably better inside. So if you just all stand to that area, and then we get a picture from the top taken. And if you're interested, if you now are interested in collaborating in one of the tasks, either in the solar or the wind task, for forecasting or generally for solar resource, then leave your email here with Yann or me, and we'll put you on the task lists, and then you can continue to get the updates on what we're doing. With that, thanks for coming, and I hope you'll stay also for the common task meeting that we're having in the afternoon, also in this room. I have a key here, and I'll lock the door so that we can leave our stuff here and go for lunch. Thanks.